We talked about how things dissolve, and we talked about the idea of a solute versus a solvent, and we talked about how things are how they dissolve and the way that they act when they dissolve. But in this particular case, the vast majority of this particular unit, we are going to be talking about solution phase reactions, which are most often referred to as double replacement reactions. And so what I need you to understand about double replacement reactions is I got to go back in time and refresh your memory. So if you would recall that the double replacement reaction was A, B plus C, D will react to form A, D plus C, B, right? One of the things that we knew for sure about these particular reactions was that these were always solutions, so they were always aqueous. And then the products we didn't really talk much about. I just said we'll talk about a later point in time, so here's our later point in time. The issue is that with double replacement reactions, there are four things that you need to consider in order to decide whether or not a double replacement reaction will occur. You may recall from a single replacement reaction the idea that the activity series of metals, you had to look at whether or not the metal was quote unquote cooler than the other metal and could replace it in a reaction in a single replacement. And this one, that's what I gave you the solubility rules for, which we'll talk about in a second. So in this case, the issue is that you have to identify one of four things that make that about a double replacement reaction. So the first thing you are looking for is if you have two aqueous products. That's one thing you have to look for. Another thing you have to look for is if liquid water forms. And a third thing you have to look for is if a gas forms. And lastly, the fourth thing you have to look for is if a solid forms. Okay? Now, you're going to hear me say over and over and over again, what are the three things that drive a double replacement reaction to occur? The answer is water forming, gas forming, or solid forming. When a solid forms, though, we have a special word for it, and we call it a precipitate. So two products that are two products are a soluble aqueous product and an insoluble solid are called a precipitate. But these are the four things that you have to keep in mind every time you write a double replacement reaction from now on. Any questions about that? These are the solubility rules. These solubility rules are the ones that I just gave you the green card for, and as a result of that, if you're thinking about taking the AP Chemistry, that's brilliant. You should have them memorized by the time we start AP Chem next year. Now, I'm going to talk about these rules in greater detail, but what you need to know is that if it says something is soluble, that means that it makes an aqueous solution. If it says something is insoluble, that means that a solid product or a precipitate forms. So for example, salts of ammonium and group 1 metals are always soluble. So anytime you see something with like a lithium, sodium, potassium, rubidium, or cesium, or francium, that will always be something that will be aqueous compound, okay? Things that have chlorides, bromides, and iodides are soluble except if they're with silver, mercury, or lead, in which case then they're insoluble and they make a solid. Chlorates, nitrates, acetates are always soluble. Those are ions. All sulfate ions are soluble except if they're with calcium, strontium, barium, mercury, lead, or silver, then they are insoluble. Phosphates, carbonates, and chromates are insoluble except in ammonium and group 1 metals. All metallic oxides are insoluble except for ammonium and group 1 metals. All metallic hydroxides are insoluble except for ammonium and group 1 metals and group 2 metals from calcium down. And lastly, all sulfides are insoluble except for ammonium and group 1 metals. So I'm going to show you how to work through these rules, but in order to do that, the next thing I'm going to do is I need to talk briefly about what a spectator ion is. So ions that do not react stay dissolved in water once the reaction is over. So what I'm getting at here is if I take A, B, plus CD and react it to form AD plus CB. And I say that this is aqueous, and I say that this is aqueous. What you should picture is in my solution, I have A ion and B ion and A ion and B ion floating around, okay? And in in another container, I have C ion and D ion, and I have some C ion and maybe some more D ion floating around, okay? But when I mix them together, there's a couple of things that can happen. One of those things could be a solid, one of those things could be a gas, one of those things could make a liquid, or they could be nothing at all. So the issue is that if I said that AD forms a solid here, okay, what you would really be envisioning is that I would have AD sitting at the bottom, and I'd be left with my C ion up here, floating around in my liquid, and my B ion floating around in my liquid. So I really have created this solid that forms at the bottom, and that's my precipitate. The other stuff is going to be aqueous. So the issue is that spectator ions that don't form the solid, so the ions that don't form the solid are what we call spectator ions. They don't actually make the reaction occur. So in this particular reaction, I would say that my spectator ions are the C ion and the B ion, okay? Now the equation that actually shows what actually happens is called the net ionic equation. The net ionic equation gets rid of the spectator ions and it only writes the equation for the thing that forms a solid in this case. So in this case, it would be A ion plus D ion, both of those are aqueous on the reactant side, will react to form AD, which is a solid on the product side. So the actual reaction that literally happens is A plus D makes AD, but we need the spectator ions to help them get there. Now I'm going to go through a few examples to show you how to do this in real life instead of just using generic letters. So here's an example of a type of reaction that you're going to have to deal with. And I'm going to walk through this with you, and I want you guys to kind of keep up and pay attention as how things go along. So the first thing that I'm going to identify is the fact that I've been told I have solutions, and anytime I see the word solutions, I have to assume that I have aqueous, that those items are aqueous. First thing I need to do is write the appropriate chemical formula. So I know that from my periodic table that I have in front of me, I have sodium, which is a +1 ion. And I also know from my memory, phosphate, which is a PO4 -3 ion. You were supposed to have memorized that last semester.
Yeah, but like it's not in my brain anymore.
It should be because you memorized it.
It was never in mine.
That's fair. All right, now, in the other compound we have calcium, which is a +2, and we have chloride, which is a -1 from, again, the periodic table that I remembered. So what I'm going to do is I'm going to go ahead and I'm going to write my reactants, which is Na3PO4, and we know it's a solution, so that makes it aqueous. We have CaCl2, and we know it's a solution, so that makes it aqueous. And because it's a double replacement reaction, I'm going to just start by switching them around. So I'm going to have NaCl, and I'm going to have Ca3PO4 okay? Now, what I don't know is whether or not these are solids or liquids or gases or they're aqueous. So I have to consult my solubility rules, that green card that you have in front of you. Okay? And I'm going to work one compound at a time, and I'm going to try to identify whether they are a solid forming, a liquid forming, a gas forming, or if they're aqueous. So I'm going to start literally with rule number 1, and I'm going to apply it to NaCl. Rule number 1 says salts of ammonium and group 1 metals are always soluble. Is there a group 1 metal or ammonium present here? Yes, sodium is a group 1 metal, so because of rule number 1, I would say that this is an aqueous compound. Okay? But I'm also going to go one step further and just continue to check. Rule number 2 says chlorides, bromides, and iodides are soluble except if they're paired with lead, mercury, or silver. So because of rule 1 and rule 2, this is a soluble compound, aqueous. Now I'm going to go ahead and I'm going to compare, I'm going to take a look at the rules and apply them to Ca3PO4 too. So I'm going to start back with rule number 1. Salts of ammonium and group 1 metals are always soluble. Is there a group 1 metal here? Or ammonium? No, so rule number 1 doesn't apply. Then I go to rule number 2. Chlorides, bromides, and iodides are always soluble. Is there a chloride, bromide, or an iodide present? No, so rule number 2 doesn't apply. Rule number 3 says chlorides, nitrates, and acetates are soluble. In case you forgot, chlorates are ClO3 minus 1, nitrates are NO3 minus 1, and acetates are C2H3O2 minus 1, in case you forgot. So, with that in mind, is there a chlorate, nitrate, or an acetate present? No, there is not. So rule number 3 doesn't apply. Rule number 4 says sulfates are soluble except if they're with calcium, strontium, barium, mercury, lead, and silver. And in case you forgot, sulfates are SO4 with a -2. So is there an SO4 present? No. So then rule number 5 says phosphates, carbonates, and chromates are insoluble. So I have phosphates, which are PO4 -3, carbonates are CO3 -2, and chromates are CrO4 -2. So are any of those things present? Yes. And what does it say about them? They're insoluble except if they're with ammonium or group 1. And in this case, ammonium and group 1 metals are not present, so that tells me that this is going to be a solid. So now I'm going to go ahead and balance this reaction, and I know that if I put a 3 here, I see ahead of time that that's not going to work. So I'm going to skip ahead and put a 6 here, and then that means I have to put a 2 here, and then that means that I have to put a 3 here, and then I believe everybody's balanced at this point. Okay? Now, the next thing I'm going to do is I'm going to write what I call the complete ionic equation, going from left to right. So, at this point, I'm going to do the first compound, which is aqueous, so that means they made ions, so I'm going to write this. Do you see how I got 6 sodium ions here? I took the coefficient of 2 and I applied it to the subscript of 3, and that told me I had 6 sodium ions. Do you see I have 2 phosphate ions here? I took the coefficient of 2 and I applied it to the phosphate, and I have 2 PO4 -3s. Okay? I need to do the same thing with my other aqueous reactant. So I'm going to have 3 calcium ions. Oops. It's aqueous. And 6 chloride ions, also aqueous. Okay, and then what I'm going to do is I'm going to go ahead and I'm going to apply to the aqueous products the 6 in front of the NaCl. So I have 6 Na+1, which is aqueous, and I have 6 Cl-1, which is aqueous. But then what I'm going to do next is I'm going to see that I have a solid, and I usually underline my solids a couple of times so that I remember that I have to keep solids together because they actually did form a solid here in this particular reaction. Okay. Now, I'm going to ask myself, what are the reactants that create my solid? What are the reactants that create my solid?
Calcium and phosphate.
the calcium and the phosphate. So those are the things that actually make the reaction occur. So I'm going to write the net ionic equation, which is the equation that are of the ions that make the solid form, which would look something like this. The other ions that are left behind are ions that we refer to as spectator ions. They're present as part of the reaction, but they don't actually make the reaction occur. And so in this case, the chlorine and the sodium are my spectator ions. Any questions about that? Is anybody still writing? Okay. Here's another example that we need to go through. So here I have lithium nitrate. I'm going to tell you lithium is a +1, nitrate is NO3 -1. I have potassium bromide, which is a +1, and Br, which is a -1. I remember that from the periodic table and the polyatomic ions I was supposed to memorize. So I'm going to write my reaction, which is Li NO3, and because I'm told it's a solution, it's aqueous, plus KBr, and because that's a solution, I'm told it's aqueous, will react to form, because it's a double replacement reaction, I'm going to get LiBr, which I don't know if it's aqueous, and K and NO3, and I don't know what state of matter that is. So now I'm going to go through and start going through my solubility rules. So in the case of lithium bromide, LiBr, I'm going to start with rule number 1. Salts of ammonium and group 1 metals are always soluble. So does that apply here?
No.
Lithium is a group 1 metal. So yes, that rule applies here, and they're always soluble, so that tells me it's aqueous. The other rule that happens to apply here happens to be rule number 2, chlorides, bromides, and iodides are soluble as well. Now, so that's aqueous. So then for the next one, I have potassium nitrate, KNO3, so I'm going to start with rule number 1. Salts of ammonium and group 1 metals are soluble. Does that apply here? Yes, potassium is a group 1 metal, so rule number 1 says it's aqueous. So I'm going to write aqueous back here. And then, but just for the sake of argument, I'm going to look at rule number 2 and identify that I do not have a chloride, bromide, or an iodide. I'm going to look at rule number 3 and note that I have a chloride, nitrate, and acetate. And I do have a nitrate, so because of rule number 1 and rule number 3, both of these produce aqueous products. Now, of the 4 things that we talk about in terms of a double replacement reaction, we have 2 aqueous products, gas formed, liquid water formed, or a solid formed. The issue is if I have 2 aqueous products formed, nothing happens. There's actually no reaction. It's literally the equivalent of me taking a bucket of water and pouring rocks into it. Nothing happens except the rocks get wet. So if I have 2 aqueous reactants and 2 aqueous products, I have no reaction forms, so I'm done with this problem. That only occurs when I have 2 aqueous products.
Did you write that N backwards?
What N backwards?
I was wondering what that is.
That's a lowercase n, sorry.
Lowercase n.
That's a lowercase n. All right, can I go on now? Because we got one more example to do. So, here we have a solution of copper 2 sulfate, and this is Cu plus 2, and sulfate is SO4 minus 2. And then we have sodium, which is Na plus 1, and hydroxide, which is OH minus 1. Now what I'm going to do is I'm going to tell you to go ahead, give you a hint, and I'm going to have you go ahead and do this one yourself. So I suppose if you were doing this by yourself, you would have hopefully correctly written the reactants, predicted the products correctly, identified that rule number 7 tells you that the copper hydroxide is the solid product. And rule number 1 and rule number 4 tells you that the sodium sulfate are aqueous products. I wrote my complete ionic equation. I then went ahead and identified what the two reactants were that created my solid product, which in this case, my solid product was the copper hydroxide. I then identified what my spectator ions were, and I isolated the net ionic equation. Do we have any questions about this?